did pretty well on the exam. I just want to go over your grades and the numbers that I put online. You know, guys, I don't use those percentages that Moodle reports. I've said this before, but I just want to be clear that those percentages, just don't worry about those, or the total course points. I can't get rid of it, so just ignore that. What you want to do pay attention to are these numbers that I put on that said to make an A, to make a B, to make a C, and to make a D. Yeah, I saw those numbers on Moodle. What that means is that if you make those grades on exam 4 and the final, then that means that you'll get an A, B, C, or D in the course. So that's what you need to be shooting for, is one of those top first 3. I mean, you don't want to make a D in the course, so that means you have to retake it. But if you're chemistry or pre-engineering or biology,
you have to make that on exam 4 and the final.
Exam 4 and the final. But remember that the final is out of 150 points, and these are percentages, not points. So for example, here I had these grades, and it says I need a 76.4 to make an A. So I have a 76.4 here on exam 4, and then I have a 76.4% on the final. All right, and then I get this 89.5, which is an A in the class. That assumes that you do all the class participation. So for example, if I have 40 points in class participation, then I'll fall short of that A. So it assumes that you get the full 50 points. Right now, you should be right at about 40. If you're at 40, you're on good track to be at 50. If you're under 40, it doesn't mean that you're not going to get 50. Just come to class, make sure that you're doing all the clicker questions and getting them as correct, mostly correct as you can. All right. That might mean that you might want to look ahead and go through those questions that are in the back of the book and just go ahead and mark the answers that are correct. You can talk to people, you can do whatever resources you need, and go through the quick test questions in the book as well. All right. I will likely also give you another opportunity to sort of bolster that credit towards the end of the semester. All right. Any questions about the grades, what they meant? I'm not going to hand back your exams today. It's going to be Monday. Sorry. All right, we're beginning now with rotation. Chapter 7 is pretty short. We'll finish it, not today, but probably next time. And then Chapter 8 follows closely with Chapter 7. And then, I think after that, yeah. And then after that, we're going to do elasticity and equilibrium. If you're pre-engineering, that's a lot like statics. We're going to do some statics problems, which are similar to what we did in Chapter 4. And that part of the exam will be take-home. They're kind of fun. It's a lot like Chapter 4, except we're going to throw in torques, where we're going to have torques and forces are in equilibrium. So you spend, engineering students, you'll spend a whole semester, actually 2 whole semesters on that, in statics and then in dynamics. So we're just going to preview that a little bit, and that portion of the exam will be take-home. So I'll give you 1 or 2 problems for you to work take-home, but it'll be a portion of your 4th exam. You'll follow what I mean? All right. But most of the 4th exam is going to be Chapter 7 and 8, which is everything that we've done so far. So we'll see kinematics again, except in a rotational frame that is moving in a circle. We'll see energy, momentum. Yeah.
Okay, posted a video on this. About angular momentum.
Yeah, that's fine. I saw actually. Yeah, that's okay. We're going to get to that because it was about conservation momentum, right? The video, but angular momentum. Yeah, so we'll get into all that. We're going to see some new math things with cross products and volume integrals integrating over a 3D surface in order to find the moment of inertia. So there's a lot of new stuff, but then mostly it's old stuff in these couple of chapters. Alrighty? So first of all, we're going to discuss rigid bodies only. Rigid bodies, all parts move at the same angular velocity or angular speed. In a rigid body, the parts do not move with respect to one another. WRT is with respect to. So a couple of things there. So this is a rotating body. It's a rigid body. Rigid means, you know, it's not squishy, right? A non-rigid body would include like fluids, things that move like jello or whatever. But on a rigid body, if I rotate it, every point on this moves at the same angular speed. So if I'm rotating this at 1 revolution per second, 1 revolution per second, that means that every point of this object is rotating at 1 revolution per second. This point here is rotating at 1 revolution per second, and any other point also, like here, 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 they're all rotating at the same angular speed. Right? Also, the parts don't move with respect to one another. That's because it's not squishy, right? That this point and this point are always going to be the same distance from one another. Those are fixed distances just because of the type of material. If you don't have a rigid body, that means the physics is a lot more complicated. So if you're dealing with fluids, for example, or objects that are not rigid. So examples of some rigid bodies. What's an example of a rigid body in circular motion? A chair. Thank you. Okay, yeah, like a tire or wheel. You think of one more? Okay, carousel, yeah. Or like that thing at the fair that you spin around on, right? Y'all ever been on one of those? Yeah, there's a bunch of those actually, yeah. But a Ferris wheel, or a carousel or a Ferris wheel. What's an example of a non-rigid body? Okay, yeah, Jello said several of these. What else? Huh? Okay, yeah, any fluid actually. So any gas or liquid. And we're not going to deal with that at all. The axis of rotation, when we get into moments of inertia, we'll be very clear about we need to define what is the axis of rotation. It's just the axis about which the object rotates. Right. And the same body can have different axes of rotation. All right, so for example, I can have several axes of rotation. Like I can rotate about this axis, right? And then I spin around like this, like I'm a ballerina or whatever. But I can rotate about other axes too. I can rotate about this axis, and if I did that, that would be called a what? If I rotate about this axis. A cartwheel. Y'all want to see? Yeah. No, I can't do a cartwheel. And I can also rotate about this axis, and that would be like a forward or a backward split. It's a lot easier to rotate through some axes, right? Like it's a lot easier to rotate through this axis than it is to put my feet up over my head going through this axis. The reason for that is your moments of inertia is different through different axes, and we'll define that in Chapter 8, and we'll actually calculate different moments of inertia. We'll see that it's a lot more difficult to rotate through different axes. Just the point here being that you can have a different axis of rotation for the same object. And just like we did in Chapter 2, we're going to define several things. So remember in Chapter 2 with kinematics, we defined position, displacement, velocity, and acceleration. That was x, v, x, delta x, v, and a. Right? We're going to do the same thing here. It's exactly the same with just a few minor things. First of all is the angular position. Our angular position, we'll typically use theta to define our angular position. The unit for the angle theta is the radian. And other units include degrees and revolutions. You'll need to be able to convert between those. Remember, for 1 revolution, which is 1 full circle, right, is equal to 2 pi radians, which is equal to 360 degrees. All right, this angle theta just says what is my, in this case, what is my angle theta from the x-axis. Now, your angular position is not some point in space, so it's not like this point. It's not dependent upon r necessarily. It just says through what angle have I turned. Right. Our angular position is also related to something called the arc, which you'll probably remember from middle or high school. This is our arc, and our arc is equal to this s equal r theta. And so if we let theta go to our full circle, we get an expression for the circumference, and the circumference is equal to what? The circumference of a circle? Right, 2 pi r. So if I let theta go to 2 pi, that as theta goes through the entire circle, you can calculate the arc, or the distance that is from here all the way around the circle, and that circumference is 2 pi r. That's where that comes from. Is that?
Have you ever heard of the unit of grads?
Yeah, I forget what is a grad.
I just know because in our surveying book, it's just like it's one of the units.
Yeah.
One of grads.
Yeah, I forget what a grad is. Let's look it up right quick.
It's some kind of European.
Oh, it doesn't even recognize it. Conversion between radians and grads. What did we do before the internet? No idea. All right. We used books and libraries, yes. Yeah, grad, 2 pi radians is 400 grads. I don't know why you use grads. Why do you use that? You use it in surveying, though?
Not really. Like I said, I think it's just a European
Thing.
survey.
Okay. Yeah, I don't know. I have a vague memory of it. Okay. If we were in pre-internet days, we would have to go to the library, and it would take us like a couple hours to figure out what a grad was, right? Okay. Now, angular displacement. If you remember before, we had angular position was x, and our position was x, and our displacement was just x final minus x initial. We're going to have the same thing for angular displacement. It's going to be delta theta is equal to theta final, or I'm going to call it theta 2 minus theta 1, or you can say theta final minus theta initial. The only difference here is that, remember with linear displacement, left was negative and right was positive. And so we're going to adopt a similar convention here, and that is that counterclockwise displacement is positive, and clockwise displacement is negative. So for example, if you have a clock, and I have my hour hand going around, and it's traveling in this direction, it experiences what type of displacement? Positive or negative? Negative. Right, so this is delta theta is less than 0. But if I'm going the opposite direction, my delta theta is bigger or smaller than 0? Positive or negative? Positive. Right, it's positive, so it's greater than 0. So I get these like catalogs sometimes. They sell like kitschy science gifts. Y'all might have seen one of these before, but you can buy a clock that goes in the counterclockwise direction. Have you ever seen that? Like all the numbers are backwards. And the idea is that a clock, when you look at it like this, is going in the negative direction. So it's measuring time backwards or whatever. Because the convention for displacement is that clockwise is negative.
Why would be that? All kind of times.
Y is what? I think, I'm not sure, Tong. I think it has to do with your right-handed coordinate system.
Yeah.
What's that? Yeah, it's the coordinate system. I think it's because if you do, we're going to talk about this in just a bit. I'm not certain that this is why. But if you use your right-hand rule, if you know the right-hand rule, we're going to see this in just a bit. But if you use your right-hand rule, you let your fingers go in this direction, and then your thumb gives the direction of the angular vector. And so this would be a positive k direction, and so they would take this to be a positive. I'm not sure that that's why they do that, but I don't know. It's my best guess. All right, so clocks go in the negative direction here. If that helps you remember. That clockwise is negative and counterclockwise is positive. Okay, so this is measured, as we've already said, in radians. By the way, you won't need your calculator in radian mode. You will not need it in radian mode. That only comes up if you're taking trig functions in radians. Okay, so in this class, you'll always need it in degree mode for this semester. Next semester, I think, we'll need it in radians. Okay, angular velocity. Before, remember, we defined this as v was our displacement over our change in time. Here, now instead of calling it v, we're going to call it omega. This is the Greek letter omega. And omega, which is our angular velocity, is our displacement, which is delta theta over delta t. So whereas before we had v, now we have omega. Oh yeah, so also if you remember before, this is an average angular velocity, right? Because it takes the angular velocity over a certain time interval, delta t, and it averages what is the velocity over that time interval. If you recall when we were looking at position versus time graphs, we could do a similarly over here. If I have a graph that looks like that, our omega average would take 2 points and find the slope between them. So it's not some instantaneous velocity, instead it averages the velocity over time. But we can find an instantaneous velocity, and it's going to be the limit of our average angular velocity, which is delta theta over delta t. And we're going to take this, and we're going to let this delta t, this time interval, go down to a particular point. So we're going to shrink it down to just a particular instant in time. So we're going to let delta t then get really, really small. Let it approach 0. And that, of course, is the definition of a what? That limit as your denominator goes to 0. No, think Calc 1. It's a definition of what? The derivative, yeah. So it's this is the same as d theta dt. So all the stuff that we did before in chapter 2, where we can take a position function and take the derivative of it to find the velocity function, and take the derivative of that to find the acceleration function, all that stuff will still hold. And we'll see some problems like that in just a bit. All right, angular velocity clockwise is negative, counterclockwise is positive, just like before. And then angular acceleration, remember before we had a was equal to delta v over delta t. Here, instead of a, we're going to use alpha. This is the lowercase Greek letter alpha. And it is equal to delta omega over delta t. All right, this is our average. And so similarly, we can define our instantaneous. That is our acceleration at a particular instant is delta, the limit. As delta t approaches 0 of delta omega delta t, which is, we've already said, is the definition of the derivative, d omega dt. Okay? And so clockwise is negative, counterclockwise is positive. So we've done all these derivations before, but we can show then, just like we did in chapter 2, exactly the same as we did in chapter 2, except now we're making these substitutions. We're saying where before we had x, now we have theta, whereas before we had v, now we have omega, and whereas before we had a, now we have alpha. So all the same stuff will apply as to what we did in chapter 2, but we're going to substitute these rotational quantities, these circular quantities in for those things. Let's just talk briefly about angular vectors, the direction of these vectors. Because if I have an object spinning, how do we define the direction of that angular velocity? I guess not in this direction, right? Because that angular velocity, if I were to say it's tangent to the circle, then the direction will be changing all along. The direction of this is actually going to be perpendicular to the rotation, and we'll find it with something we call the right-hand rule. right-hand rule, you take your right hand and you let the fingers wrap in the direction of the rotation, and the thumb gives the direction of the vector. We'll use this in the next chapter when we do cross products. And I think just one of you is like Calc 3, is that right? Just one? Shoot, James? You took it already. Anybody else in Calc 3? Y'all don't have to take Calc 3. Chemistry majors?
Yeah, we have to take it for one.
Oh, okay. And engineering. Who's engineering? Y'all have to take different calculations, right? Yeah. So you'll take Calc 3. Anyway, so you'll do cross products there, and you might do them a little bit differently than we do them here, because we'll focus a lot on the direction of vectors and what have you. I think y'all do the matrix thing, right? Yeah. So anyway, so we'll use the right hand rule. We'll let our finger go in our fingers wrap around in the direction of motion, and then our thumb gives the direction of the vector. So for example, if I have this object traveling around in this direction, what is the direction of the angular velocity? If it's rotating like this, what is the direction of the angular velocity? It's going to be straight up, right? I let my fingers wrap around in the direction that it's traveling, and then my thumb gives the direction of the angular velocity. So my angular velocity for an object spinning like this would be in the positive y direction. Right? If it were spinning like this, what would the direction be? Right? It'd be exactly opposite. So if my fingers wrap around, it would be in the negative y direction. It's not going to be terribly important right now, but we'll see it again in chapter 8 using the right-hand rule. And that's all wrapped around this idea that we're using a right-handed coordinate system. If we were using a left-handed coordinate system, then it would be opposite that. You'd use your left hand and your vectors would be opposite directions. It's just a system that we use to describe vectors. Not terribly important. But it is important, but it doesn't matter really which one you use, just as long as you're consistent. Okay, so if you remember, we had to derive those equations from chapter 2. I know this is really fast. It's fast? It's too fast? A lot of this is review, so that's why I just want to sort of zoom through it, and then we'll get into some problems. So we derived those equations based on the definitions, that is that A was dv dt, and then you remember we say dv is a dt, and then we integrated both sides, and we got that v equal v naught plus at. You don't have to write this down, I'm just reminding you that we had that derivation, and then we could take this and substitute it into v is dx dt, and then integrate, and then we get that x equal x naught plus v naught t plus 1/2 at squared. Remember that sort of? Using our integration constants. You're not going to have to do the derivations, but I just want to remind you. So anyway, we got two equations for angular acceleration, or position with constant angular acceleration, and that was that v equals v naught plus at, and x equals x naught plus v naught t plus 1/2 at squared. We can do the same thing for rotational motion, and we'll get omega equals omega naught plus alpha t, and theta equals theta naught plus omega naught t plus 1/2 alpha t squared. These will be on your equation sheet. They are already on there, so you'll have them for various problems that will work. But you'll certainly see a kinematics problem. It might be more in line with something that we do in chapter 8, where it's sort of part of a bigger problem. I'll show you some questions like that in a bit. Okay, but these are our equations. As was usually the case in chapter 2, the initial position is usually 0, so we usually just leave that off. And again, if we think about this in terms of like changing our linear equations to our angular equations, I've already written this, let me write it again because it's worthwhile. Basically, we're taking x and replacing it with theta. We're taking v and replacing it with omega, and taking a and replacing it with alpha. So we have theta, omega, and alpha that we use to describe the position of objects moving in a circular path. You can also translate these into linear quantities. If I have an object that's moving around in a circular path, we've already said that the angular velocity here is related to tau here. How do they compare? Is this angular velocity bigger, smaller, or the same as this angular velocity? It's the same. They're both rotating around at the same rate, 1 revolution per second or whatever. But how do their linear velocities compare? Is the linear velocity in meters per second, is it bigger, smaller, or the same here as it is here?
Bigger also.
It's bigger, right? Y'all ridden on a merry-go-round? Right, on a merry-go-round, you go to the edge, it feels like you're zooming, right? But you go and you stand in the middle, and it's like you just stand there, right? Because you're not even moving, you have no linear velocity if you stand in the middle. You might be spinning, but you're just spinning like this. But then you go to the edge, and you're covering this big circle in the same amount of time. All right, so your linear velocity, for example, is related to your angular velocity by the radius. And if your radius is bigger, like on a merry-go-round, then you're going a lot faster. We've already seen this sort of when we did the arc of a circle. Remember that was S equal R theta? Right. Well, it shouldn't be a big reach for you then to say, well, if I divide both sides by t, then that's going to give me the expression for v. And so v will equal to r omega. And then if I divide both sides by t again, I get an expression for the acceleration, which is going to be r times alpha. So all of these quantities are related to one another by the radius of motion. So if I wanted to know, have a certain object spinning at a certain angular velocity, if I want to know the linear or the tangential velocity at a particular point, then I can just multiply times the radius. We'll see that come up in just a bit. Let's try this quick test. I have a tire. It's on a balancing machine, you know, one of those things you put a tire on, it spins it, and you put the weights on it in order to make it not wobble. Anyway, so it spins, starts from rest, turns through 3.2 revolutions in 2 seconds before reaching its final angular speed. Calculate its angular acceleration. Notice the units here are different. I'll remind you of the equations. shoot for about 15 more seconds, yeah. I'm gonna stop at 2:35. Just 5 more seconds. Just guess if you don't know. Oh goodness. Okay, let's see. We're sort of all over the board. I think the answer is B, though. Let's see. So on these questions, guys, we just want to pick out what are the known values and then find the appropriate equation, and then from that find what it is that we're looking for. So a couple keywords I want to pick out. It starts at rest. That means that what is equal to 0? What is that W looking thing? The omega naught? Yeah, omega naught. So omega naught is equal to 0. It says it turns through 3.2 revolutions. That means theta is 3.2 revolutions. I've noticed that all my units here are in radians, so I need to convert that to radians. But actually, I'm going to hold it in revolutions for now. We'll go through the calculation, and then we'll convert it to radians. Though many of you probably converted it at this point, right, to radians? Did y'all convert it to radians here? Okay, maybe not. Okay, so then I have a time of 2 seconds. Before reaching its final angular speed, and I want to know the angular acceleration, alpha. Okay, so I have these equations over here that I know are true. I'm looking for alpha. I have omega naught, theta, and t, so I'm going to use this one right here. So I say theta equals omega naught t. This goes to 0 because omega naught equals 0. And I have theta 3.2. T is 2 squared. That's going to be half of 2 is, or half of 4 is 2. 3.2 revolutions over 2 seconds squared equals alpha. That's 1.6 revolutions per second squared. However, I know that the units here are not right, so D is not the right answer, as a lot of you put. You want to convert this into radians. In 1 revolution, there are how many radians? Right, there are 2 pi. 2 pi radians. Those cancel, leave me with radians, which is 1.6. Usually when you write radians, you don't write it as a unit. It's not a true unit, so you would usually just write it seconds to the minus 2. Though I will often list it as radians per second squared. But if you ever see it just not written as a unit, that's why. It's not really a true unit. So 1.6 radians per second squared, or excuse me, not 1.6. It's 10.1. 1.6 times 2 pi is 10.1. So B is the right answer. Let's see, a lot of you put D. Probably just didn't do the conversion. A. I don't know why you put A. I'm not sure. Does anybody illuminate? Oh, you guessed. Okay. All right. Okay. Could see a problem this simple, but likely it's going to be embedded within some larger problem where we're applying Newton's laws and looking at the rotation of an object. We'll get into that in Chapter 8, but I just want to present it here, and then we'll come back to it in Chapter 8, all right, for kinematics. But a lot like what we did in Chapter 2 as well. But we're not doing all the free fall and all that business. We're just doing something rotating. A lot simpler, I think. Let's do the concept test. These last 10 or 12 minutes or so. It's in the back of your book. I asked a similar question earlier. Bonnie and Clyde are on a merry-go-round. How do their angular velocities compare? Clyde's at half the radius of Bonnie. I'll stop at 105. 105. Very good. I think it's the right answer. So if you're on a rigid body, this is one of our definitions of a rigid body. Every point travels at the same angular speed. Remember that goes back to the chair. And if you're rotating, every point from this chair is rotating at the same speed because it's rigid. All right, now asking who has the larger tangential or linear velocity. We call it tangential because the direction of the vector is tangent to the circle. But who has the larger linear velocity? Bonnie, Clyde are the same. All right, stop at say 40 seconds. Let's guess if we don't know. Very good. So Bonnie has a higher speed. You want to see our camping pictures? I don't have a joke. You want to see our camping pictures? No, I don't have those yet. I'll show you. Y'all care to see the camping pictures? We went camping last weekend. I think I told y'all. Just take a second. Let's see. We went to Tickfall State Park. Y'all ever been there? It's like our favorite state park. Yeah. We went canoeing. This was out on the Tickfall River. That's my little girl, my little boy. He fell during the night, one of the nights, and he fell like face first on the asphalt. Tripped on something, running around, acting like a crazy person. Fell. Scrapes all over face. See his cut lip, cut nose. We went canoeing. It was a nice weekend. That was this is our canoe selfie. It's a selfie, I don't know if y'all can tell. They had like a craft there at the nature center. A little girl did it. That's a squirrel, a little paper bag squirrel. That was our campsite. We went geocaching. This is where we went geocaching. You ever been geocaching? It's fun. You ever been? You have a GPS. If you have a smartphone, you can do it too. But like around Thibodeau, there are caches that are hidden. They're like little treasures you can go and find. And you can download their coordinates on a website, geocaching.com. And they give you like little hints and stuff to find it. And then you go and you like take a toy and you leave something or trick you sign a lock. It's a lot of fun. There was a cache near this sign. And that was a selfie we took. That was just my kids. All right. You're welcome. All right, let's see. Oh wait, where's my clicker thing? Did I get rid of it? Sorry. Okay, Okay, so suppose that the speedometer of a truck is set to read the linear speed of the truck, but it uses a device that measures the angular speed of the tires. And that's what your car does. It measures how quickly does your tire rotate, at what angular speed, how many revolutions per second. And then it takes the diameter of that tire and it converts it into a linear speed. That's what your car does. If you have a speedometer on your bicycle, that's a lot easier to think about because it has a little magnetic detector. But your car works in the same way. But let's say that you put bigger tires on your truck, like you put those big monster tires on it, with bigger wheels as well. How does that affect your speedometer reading as compared to the true linear speed of the truck? Does the speedometer say that you're going faster than you are, does it say that you're going slower than you are, or does it still read the true linear speed? I'll stop at 45. Just guess if you don't know. Still missing something like that. All right. I think it's the right answer. Let me show you. Let's imagine that I have this tire right here. All right. It goes around at a certain angular velocity. But then I put a bigger tire. I'm still going around at the same angular velocity. All right. So on both of these, the car would read the same speed, right? Because you're going around at a constant angular velocity. But the car thinks that you have a wheel that's this size. Your speedometer, the computer, your speedometer thinks your wheel is this size. So this wheel, is it going to cover more distance or less distance in the same time as this wheel? More or less distance for this wheel? It will cover more distance in one revolution, right? A bigger wheel, you spin it around, it goes a further distance than a smaller wheel. All right, so this bigger wheel is going to go faster or slower? Faster. It's going to go faster. All right. So at the same rate of rotation, omega, if they both have the same rate, the bigger wheel goes actually a further distance in the same amount of time, so it goes faster. So that means that your car with a bigger wheel will actually go faster than what your speedometer says. Follow me?
Which means I'm going to put big tires in my car so I go faster.
Well, yeah. No, that's not what it means. It means that you're going faster than your speedometer says. I guess it must be more difficult for your car. I'm not sure about that. Like, can you go faster just by adding bigger wheels? Is that what you're asking?
Yeah.
I'm not sure.
You can if you like hit your speed limiter, I guess. Like, I don't know what some vehicle speed limiter is, but my truck's like 91, and I put bigger tires on it, so like I can go like 96, 97.
Cars have governors on them that limit your speed?
Yeah. And right limiters too.
And do it now? Oh,
And a
Revolution?
like a
Really?
limiter.
Y'all know this? Like, what happens if you get to it?
It like puts. Like, have you ever been in a golf cart and like tried to slam the pedal down, and you know you get up and then it
Oh, okay.
It'll cut off the.
Yeah.
I'm pretty sure. And then once you get under a certain speed, it'll.
I didn't know that.
Y'all know why factory cars have the governor though?
Some people.
To prevent the engine from...
I don't know.
No, it's actually because tires are not rated, like for most vehicles, it's because tires are not rated to go faster than like 120 miles per hour, so they put the governor so you can't go faster.
Yeah,
And
a
I
lot of
put
cars
low
can
end.
actually like go a lot faster.
It's got very little, public safety.
Yeah.
With everything, those tires don't flow from the pressure.
Oh, cool. I didn't know that. That's interesting. I'm more amazed that y'all know that. Because you all know it. Okay. An object begins to rotate with a constant angular acceleration. If this object rotates through an angle theta in the time t, through what angle did it rotate in the same time, or in the time 1/2 t? So it rotates through theta in time t. What angle does it rotate through in half t? So how is theta related to t? Is it a linear? Is it quadratic? Is it square root? What is it? let me remind you of the expression for theta. Is theta, especially if it begins at rest, that means that omega naught equals 0. So it's theta equals 1/2 alpha t squared. And I want to know if it goes through angle theta in time t, what angle does it go through in time 1/2 t? This theta is proportional to t squared. It's a quadratic relationship. Okay, let me try it again. So theta is proportional to t squared. Right, so in time t, I get angle theta. But what happens if I have time 1/2 t? What happens to theta? What angle do I go through in time 1/2 t? If I have that time, what happens to my angle theta? So rethink your answer, most of you. Okay. I'm going to stop in about 5 seconds. Stop at 2:30. Okay, very good. D is right. It's a quadratic relationship. So if I have the time, since time is squared, I quarter the displacement. Object begins to rotate with a constant angular acceleration. Object has an angular velocity omega. What was its angular velocity at time 1/2 t? To remind you, omega is equal to alpha times t. That's assuming you know that it's initially at rest, so omega naught equals 0. So if I have the time, what happens to omega? I'll stop at 50. Very good. Sorry, no jokes this morning. I can't think of any right now. Let's try this, then we'll make this the last one. The fan blade is slowing down. What are the signs of omega and alpha? Remember our notation that clockwise is negative and counterclockwise is positive. Now this object has an omega that is in the clockwise direction. And so I want to know, and this blade is slowing down. So it's traveling, but it's slowing down and coming to a rest. So I want to know, what are the signs of omega and alpha? This will be the last one. Remember that slowing down doesn't necessarily mean that your acceleration is negative. Slowing down is more, how is your acceleration related to your velocity? Is it opposite or in the same direction as your velocity? We had that stuff in chapter 2 about this. I'll stop at 1:30. Oh, looks like you're all in right now. Omega is negative because it's in the counterclockwise direction, but alpha is positive because it's slowing down. So alpha is opposite omega. Right. velocity and acceleration in the same direction, speeding up. Velocity and acceleration in the opposite direction, slowing down. Just because you have a negative acceleration doesn't mean you're slowing down. All right, we'll come back to this. We just have a few more. And we just have one more topic in this chapter, and we're going to finish up chapter 7. If you're looking at the homework, you can go and look at the first 4 or 5 problems, all those on kinematics. If you get to centripetal force, you can stop. But I would go ahead and look at those homework problems.